Ohayo gozaimasu, good morning, and welcome to the first session of the Quantum Cybersecurity Seminar Series, co-organized by OIST and the Asia Society Japan. This series of presentations is part of OIST's strong commitment to research on advanced quantum and post-quantum cybersecurity. We aim to connect a global network of top quantum cybersecurity experts to a Japanese audience. Our seminar series will feature one speaker every few months, focusing on a different aspect each time. I hope that this series will help familiarize you with global quantum cybersecurity developments and future trends, and that it will spur your interest to our future events as well. I'm excited to say that for today's session, Dr. Alexander Ling from the Center of Quantum Technologies in Singapore will talk about satellite quantum communication and impact on cybersecurity. The navigator of today's event will be Dr. Artur Ekert, who, I'm sure as many of you know, is a pioneer of quantum cryptography. His research interest extends over most aspects of information processing in quantum mechanical systems, with a focus on quantum communication and quantum computation. His 1991 paper generated a spate of new research that established a new area of physics and cryptography. It is one of the most cited papers in the field and was chosen by the editors of the Physical Review Letters as one of their milestone letters. Artur is a professor at Oxford University, professor at the National University of Singapore, as well as the founding director of the Center for Quantum Technologies in Singapore. And last, but not least, holds an adjunct professorship at OIST. Artur, the floor is all yours.
So this is essentially a webinar that is supposed to inform those of you who are interested in quantum technologies and security technologies about what may wait for us in the not too distant future. So we are talking about security in the quantum age. And of course, security in quantum age will have all kinds of different aspects. And today we are going to start with one of them, namely with quantum communication on a large scale and involving satellites. So it's my actually great pleasure to introduce our first speaker in this series. It's Alex Ling from CQT in Singapore. Now, let me briefly introduce Alex. Alex has been associated with the Center for Quantum Technology pretty much since its inception in Singapore. So he was a PhD student at NUS, National University of Singapore, and got his PhD in 2008. And then he worked as a research assistant in the United States for a while, for about a couple of years or so, with the University of Maryland and NIST. And then we managed to attract Alex back to Singapore, and since 2010 he's been associated both with the National University of Singapore and the Center for Quantum Technologies. Now, Alex is one of the pioneers, if not the pioneer, of quantum satellite communication. He shaped the national program for satellite communication in quantum domain in Singapore, and also established very close collaboration with our colleagues, mostly in the United States and United Kingdom. He's also a person who nicely bridges two different communities. He's excellent researcher, but he's also very much aware about translational research, how to take the best we have in quantum technology, the most mature aspects of quantum technology, and put it into practice. So he's a co-founder of two startups, and one of them, Spectral, that will probably feature in his talks, is focusing on satellite quantum communication. So I think I will leave the floor to you, Alex, now. And so please do tell us about what is quantum communication via satellites? How does it work? And I'm sure there will be many questions that I will try somehow to we'll take them later from the audience, and I will then we'll talk and discuss about those questions later on. So Alex, the floor is yours.
Thank you, Arthur, and thank you to OIST and Asia Society Japan for inviting me to give this talk. It's a great honor to be the first speaker in the series. Now, let me just share my screen. Okay, very good. So, what I'm going to talk about today is about quantum communications using satellites. And I'm going to give you a motivation of why we want to go into space and how we think this can actually affect cybersecurity in the future. And then I'll give you a brief snapshot about the different technologies that groups around the world are developing. And then we'll end with a little peek into some of the results that we have obtained in Singapore. Now, just to kick off the conversation, the screen you're looking at here, the first page, is actually a photo of our small satellite, SpookyOne. And you can see SpookyOne in the center, and it is being deployed out of the International Space Station. So as the satellite carrying a quantum payload was coming out of the space station, the astronaut actually took a photo of it and shared it with us. So it's actually really nice to see the work of the PhD students and the postdocs, coming together. And speaking of the PhD students and the postdocs, I just want to thank them. They are a small group. You can look at them here. Occasionally, we climb to the rooftop of a building on the university. In this case, we are next to our little radio antenna that you can see on the right of the picture. This radio antenna is how we actually communicate with the small satellite. And Robert Beddington, who is the chief systems engineer, is actually holding a live scale model of SpookyOne over here. And you can see the port of Singapore in the background, where there's, it's one of the busiest ports in the world with lots of ships. And those ships are all also, they happen to also use the same radio frequencies with which we are communicating with the satellite. And so this gives you an impression of the amount of challenges that we have when we want to talk to satellites in general, especially from an urban environment, because you have to contest with all these other users of the same radio frequencies. Now, let's move on a little bit and let's talk about quantum technologies on satellites. And it's a very natural question to ask: is why should you care about academics putting quantum technologies on satellites, right? And how does this actually affect cybersecurity? Well, the main reason is the rapid progress that people have been making into quantum computing itself. And in this picture over here, you are looking at one of the first chips that one of the companies have made for a quantum computer. There are several qubits on this chip, and every few years or every few months, the quantum computing community is reporting rapid progress in its development. And while this is really exciting for a lot of applications, such as the search for new drugs, simulating new materials, or trying to solve optimization problems, one of the challenges that the quantum computer presents to the community, to the global community, is that it can actually factorize the products of large prime numbers very fast. And this sounds really strange, that one should be concerned about this. But the main reason is that in cybersecurity today, the public key infrastructure with which we authenticate, with which we encrypt our data, relies on the fact that a classical computer has a lot of challenges in trying to factorize the products of prime numbers, right? And so using this difficulty, we have actually built an entire infrastructure for communications privacy. Now, the challenge is that if a quantum computer really takes place that can actually factorize these products, then the underpinning assumptions about what makes our communication secure and private will actually fall away. And so this is the reason why, in the quantum technology community, there's also a group of us looking at how to actually, protect against the erosion of our communications privacy. And now the concept is that we believe that there is going to be an era in which quantum computers are widely available. And so we're looking for something that's quantum safe, right? And so if you sample the community of practitioners who are building quantum computers, and you ask them, when do they think, a quantum computer capable of breaking encryption, the conventional encryption that we are using today, you will get a variety of opinions. And this is actually captured in a very nice report called the Quantum Threat Timeline. This is run by Professor Mike Mosca in Waterloo in Canada. And he actually put together a really nice report where he surveyed, quite a number of quantum computer experts. And you can look at this graph over here. And the question was, when is it likely that a quantum computer could break RSA 2048 in 24 hours. So RSA 2048 is one of those algorithms with which we are encrypting a lot of our data today. And you can see that, of course, in the first 2 to 3 years or 5 years, most experts do not think that this is possible with a quantum computer. But the likelihood, the consensus is that the likelihood of such an event happening over the next 2 to 3 decades is growing. Right? And this is something that we should be concerned about, because when we think of the entire cryptographic life cycle, right, of how we want to protect our data, we need to think about the time it takes for us to migrate from existing crypto systems to new crypto systems. And after that migration is done, we have to think about the lifetime or the shelf life of this data that we want to protect. And hopefully, the combination of the migration time and the shelf life is shorter than the time in which the threat will manifest itself. And so if you look at this figure on the right, what is of concern is that the threat timeline is relatively short, actually. If you think of the kinds of data that individuals and governments need to protect over decades. For example, for individuals, private health data, these are things that will actually have to survive for the lifetime of a person, if not beyond. So given the likelihood that a quantum computer capable of breaking RSA is going to be manifesting itself in 2 to 3 decades, given also that the migration timeline typically for new crypto products is on the order of about a decade at least, these threats become quite real. And so now with this understanding, we are hoping that the community of experts can actually move a little bit faster in selecting new cryptographic systems that are quantum safe. Now let's take a little look at what we think is quantum safe and what works in the era when quantum computers are going to be widely available. So NIST, that's actually the organization in the US that's in charge of selecting crypto products and establishing cryptographic standards, actually published a nice table a few years ago. And over here, they show some of the common algorithms that are found in almost all computer systems. And then they talk about the effective strength that you have in the presence of a conventional computer and in the presence of a quantum computer. And you can see that in the first 4 rows, right? For example, the RSA or the ECC kind of crypto systems, they actually provide essentially zero security in the presence of a quantum computer. Whereas for, the AES systems, there is still a little bit of a security, right? So one can actually argue that even in the presence of a quantum computer, the AES systems are actually quantum safe. Now, the main difference between the AES systems and the other algorithms, the RSAs and ECCs, is the fact that AES is a symmetric cryptographic system, whereas the others are based on the difficulty of things like the factorization, finding the factors of the products of large prime numbers. So one way to think about it is to classify the first 4 rows, the first 4 algorithms as asymmetric key systems, while as the bottom ones are symmetric key systems. And, on the face of it, it looks a little bit funny why this is the case. But the main reason is that for a symmetric key encryption system like AES, what is necessary for it to work is that the 2 parties that are communicating need to share a secret key, right? And if these 2 parties are already sharing a secret key, there is some kind of shared secret that no amount of computing power can break, right? So this is the main reason why AES is actually quantum safe. Of course, in a widely distributed network like the internet that we are using today, how do those 2 parties actually get those secret keys without ever having met before? They use RSA or ECC to distribute those initial seeds. And this is the main reason why we believe that although AES is quantum safe, the entire infrastructure for distributing those secret keys is not quantum safe, right? And this is what spurs the community to try and look for this new quantum resistant methods for distributing secret keys. Now, I want to give you a little bit of a cartoon picture of how some quantum technology could actually work in securing this infrastructure, right? And I think one of the most important things that I want to do with this slide over here is to dispel any notion that we are using quantum systems to distribute a message. Because what we're really talking about is quantum key distribution, where we are going to use the exchange of quantum signals to generate the secret key for something like AES. So if you look at the first row of graphs, right, of pictures, on the left, you have a plain text, right? Let's say there is a transmitter, someone who wants to send some message, we call a plain text, over to someone else over a public channel. So what happens is that assuming these 2 people already share the secret key using the AES system, they can use the system to encrypt, create a ciphertext, and in principle, the ciphertext can be sent to a public channel. And then the recipient can use AES to actually reverse out the ciphertext and then get the plain text. The role in which the quantum key distribution devices play is that they can actually supply secret keys to the AES system, right? So this is actually how it would work. And so what we're trying to talk about in quantum key distribution is that we want to build this hardware, right? This quantum key distribution transceivers. And then we actually want to exchange quantum signals and use them to actually generate the secret key. Of course, this is only the first step. There are actually other, communication requirements as well. In fact, there's actually a lot of classical communications involved in quantum key distribution, because what happens is that when you transmit and you measure the quantum signals, you need to convert those things into a final string of 1s and 0s that the receivers, the transmitters and receivers can use. And this requires communication back and forth, right? So you need to estimate the errors in your quantum measurements. You need to correct for those errors. During this process, some information is leaked out to the environment. We assume all of this information falls into the hands of an eavesdropper, and so we need to amplify the privacy. And in the end, we can actually get a shorter string of 1s and 0s that we believe to be secure. So this is actually how it would work and how QKD would plug into some kind of cryptographic infrastructure. And in this next slide over here, I just want to show you a really popular picture about QKD, which we can find on the internet. And this picture gives you an idea of what is actually happening when we talk about the QKD transceivers, right? So on the left, you always have a transmitter, which we'll call Alice. And on the right, there's a receiver we call Bob. So what Alice and Bob are doing is that Alice is transmitting quantum signals to Bob. Bob is measuring them. And then by a process of communication, back and forth communication, they convert their quantum signals into a series of 1s and 0s. Typically, in quantum key distribution, what is required is that Alice must only send 1 photon at a time to Bob, right? Now, this is actually quite challenging. There's only 1 or 2 methods with which you can actually transmit single photons like this reliably. most of the commercial off-the-shelf QKD systems approximate the single photon regime by using lasers. And what they do is they take the laser and they send laser pulses, and then they attenuate the laser pulses until the fact that most of the time the laser pulses are empty. Sometimes it is one, right? And in this way, they can actually approximate the presence of a single photon. But what's really important is not just the presence of a single photon, it is also the fact that you need to do some encoding into the properties of the photon. So in this picture over here, what Alice is doing is she's choosing to use the polarization, all right, of the photons. So if you think about what a photon is, it's just a packet of energy of light, right? And this packet of energy, because it's light, it is electromagnetic vibration, and you can actually imagine that the vibration can be in any plane, right? It can be vertical, it can be horizontal, it can be at 45 degrees. And so what Alice has to do is she has to choose what is the plane of vibration for this photon, right? And then she will transmit over to Bob, and Bob will try and guess what Alice has transmitted, and he will try and measure it. And through this process, they will actually end up with a string of ones and zeros that they can actually use in symmetric key systems. So this is the cartoon picture. Polarization is not the only degree of freedom that you can use with photons. You can use many other degrees of freedom, such as special modes. You can actually play tricks with the traveling time of the photon. So sometimes we call these time bins in the community. But polarization is usually the one that we think of and we try to implement. And the very first, quantum key distribution protocols from 1984 actually use polarization as well. So now that we have talked a little bit about the motivation of why we want to have a quantum safe network and how we want to use quantum key distribution, we should actually try and put all of this bits together, right? And there's actually two ways to try and get quantum safe communications going. One of them is quantum key distribution, which I've just spent the last few minutes talking about. But the other approach is to find some new algorithms that are believed to be resistant to a quantum computer. This is known as post-quantum cryptography, or PQC, right? And there's actually an ongoing effort right now led by NIST to try and identify some of these algorithms. Now, the view from Singapore is that a future quantum network, a quantum safe network, would actually make use of both of these technologies. It's not going to be entirely just quantum key distribution, and it's not entirely going to be just post-quantum cryptography. And what we're trying to do is we're trying to understand, what are the strengths and weaknesses of these two different techniques and try and put everything together. One of the exciting things about quantum key distribution is that because you're exchanging quantum signals between the transmitter and the receiver, the security assurances are actually very strong. Remember, I talked about how the quantum signals are at the single photon level, right? And so when you encode everything at a single photon level, it's actually not possible for an eavesdropper to copy out that information perfectly and without revealing itself, because any attempt at measuring the single photon would actually alter its state. So QKD provides a tamper-evident way of transmitting signals. But of course, the drawback is that you need to transfer those quantum signals. And so you need fixed sites, like you need optical fiber for the photons to travel along, or you need telescopes on the sites looking at each other. And this kind of fixed infrastructure is not easy for mobile devices. It's not easy for IoT or edge devices. So what we're trying to look at in Singapore is how to actually blend, this PQC technologies, which is very friendly to these IoT and mobile devices, and how to actually combine them together with QKD. So many countries have projects like this. In Singapore, we also have a project. We call this the National Quantum Safe Network. And we have just issued the letter of award for the project team that's going to set up this network. if you look at this little cartoon picture, this is a map of Singapore, if you would. And what we're going to start with in building this quantum safe network is NUS is roughly in this location. And the other big university is Nanyang Technological University in the west. And we're going to link them up with optical fibers, and we're going to install QKD appliances. And we have a set of commercial and government partners that are going to join us in providing test sites so that we can actually test out all the reference use cases. And so through this quantum safe network, we hope to put in place QKD appliances. We hope to test out the PQC use cases and to try and see how we can actually blend everything together. And in the longer term, one of the things we have to be concerned about is that because quantum key distribution does have to go over optical fiber, we always have to be concerned about the scattering losses inside the fiber, right? And this is why Singapore is actually a very good place for us to test out QKD technologies, because the island is only about 40 kilometers across. And over 40 kilometers, the fiber losses are manageable. But if you're talking about larger countries or larger distances, then you often see graphs that QKD people talk about on like this, where your secret rate of generating secret keys will fall off very rapidly after a certain amount of losses has happened. And so if you're talking about building a quantum key distribution network that spans the globe, it's very difficult to do it over optical fiber. There are some ideas on how you can actually build quantum repeaters with which you can re-amplify the quantum signal, but those are research which is in the very early stages. What we do know is that using satellites, however, we can actually link up these networks around the world much more effectively and much more quickly. In fact, there is quite a few efforts around the world now to demonstrate quantum key distribution from satellite to local area networks, and then to use the satellite as a node for linking up the different networks. And so in our own concept in Singapore, we also would like to have a quantum key distribution capability through satellites, which will communicate with telescopes that are plugged into the metropolitan network. And now this is where I want to switch gears a little bit and now start talking about why we want to put this technology in space. Now, if you think about QKD technology in satellites, especially how you want to communicate with the ground, right? There are actually four basic ideas that you can pursue. One of them is called the uplink. You can put a quantum transmitter on the ground and transmit signals to the satellite, and the satellite is just a receiver. This has some advantages in the sense that the receivers for quantum signals are just solid state detectors that you can get commercially, and so it's actually quite easy to put them on a satellite. Whereas the transmitters usually are a little bit more involved, and people actually have a challenging time trying to get them space qualified. The challenge is that you cannot have a satellite that's very far up in the altitude, because there is this what we call the atmospheric effect. There's going to be a lot of turbulence near the transmitter, near the ground level, and so this will actually cause a lot of photons to stray off, right? And so for about 500 kilometers of altitude, you compare an uplink model and a downlink model, you will actually suffer about 10 dB more loss in the uplink, right? And this is why a lot of the quantum communication missions are actually pursuing downlink models, where they will actually put the transmitter on the satellite. Now, in the uplink and downlink model, the idea is that the satellite will fly over one ground station, right? Carry out quantum key distribution. Now you will have one set of keys with this ground station, and then the satellite will then fly around to another part of the world and repeat with another ground station. Now the satellite will then have two secret keys, right? And you can actually add them together and broadcast them. And then, what is going to happen is that the two unique ground stations that have been communicating with the satellite, they can actually reverse out each other's keys, and then they can carry out secure communications that way. This requires the satellite to be a trusted node, right? So, this is sometimes seen as a weak link, but of course, if the satellite is actually being operated by one of those ground receivers, then it's actually not so bad, because those two people who are communicating, they need to trust each other anyway. However, if you want to move into a situation where you don't want to trust the satellite at all, then one of the techniques is actually to use a flavor of QKD known as entanglement-based quantum key distribution, which happens to be the one that Artur actually developed in 1991. And the idea is that you will put a source of entangled photons on the satellite, right? And this entangled photon source will produce two photons, right? They have very strong correlations, and you can transmit them down to two ground receivers at the same time. And in this case, you don't have to trust the satellite, because the two ground receivers can measure their own signals, and then they can talk to each other to see how strong the correlations were. And through that process, convert those correlations into a shared secret, the secret key that they're going to use for encryption. So this is actually one model. The drawback at the moment is that we really require the two ground stations to have the same line of sight to the satellite. So it's not going to be something that allows us to, say, distribute signals, if the two ground stations are on opposite sides of the globe, for example. And of course, another archetype is if you want to do inter-satellite communications, if you want to secure data links between satellites, which could actually become quite important in the future as we are talking about larger and larger constellations of satellites that are going to be orbiting the Earth. Now, all of this sounds, really futuristic, but it's actually been proven. Our Chinese colleagues have been extremely successful. They've actually, built a quantum communication satellite called MISHUS that launched in 2016, right? And it's been fully operational since then. And the MISHUS satellite has been really successful in showing all the different archetypes that I just talked about. It carries out, it has a traditional, quantum key distribution receiver, right? It has a quantum key distribution transmitter, which can transmit those attenuated laser pulses. It also carries a source of entangled photons, right? And so this satellite has actually shown all the primitives that we require for building a global quantum network using satellites. And so there's been a really large number of publications that have come out of this satellite mission, which is really, really beautiful. And the other thing is they're actually using it to also communicate across long distances. For example, in this picture on the left over here, on the ground, this line over here that you see is actually the first iteration of the Chinese QKD backbone. This is a fiber-based system which links, Beijing down to Shanghai, right? And there's lots and lots of trusted nodes inside there. But what they're using with the MISHUS satellite is that they've used it to also connect this backbone to remote parts of China. They've also recently been using MISHUS to distribute quantum signals to ground receivers in Europe, in Canada, in other countries, to demonstrate intercontinental QKD. So this idea is actually feasible. It has actually been demonstrated. And if you look at what other countries are doing around the world, the technology is developing quite quickly. Japan itself actually has the Socrates satellite, which was also launched around 2015. And Socrates actually, if I'm not mistaken, actually managed to show that transmission at close to the single photon level is actually possible. So what happened was that there was an optical transmitter that transmitted signals down to a ground station in Tokyo itself. And so this is actually quite interesting because a lot of the MISHUS, the Chinese ground stations, are actually in more remote locations, right? Where one would think that the sky conditions are actually a little bit more favorable. Whereas the Socrates mission actually transmitted the signals down to a receiver in an urban environment. And so that's actually tells you that even quantum key distribution to urban environments is actually something not impossible. It can be done. And so These precursor missions have spurred, other concepts that countries around the world are pursuing, like KeySat from Canada, QKD-SAT and Quartz from the European Space Agency, and the Chinese colleagues themselves are also planning on building the follow-on missions to Niches. For example, they want to test a new concept with a larger satellite at 10,000 kilometers, whereas Niches was orbiting the Earth at 500 kilometers. And the idea is that if you go higher up to 10,000 kilometers, you will have more orbital time over the optical ground station. And so hopefully you will be able to actually exchange more secret keys. Now, the missions on the left are actually quite large. These are really large size missions, traditional size satellites, several hundred kilograms. Niches itself was about 600 kilograms. There is another group of people, which I'm really active in, and these are people who are trying to bring the same technology and capability to small satellites, what we call CubeSats, right? And we've done quite a bit of studies over the years to show that CubeSats are actually capable also of transmitting quantum signals from space to ground, right? And so the idea essentially is that, if you look at the conventional satellites, like the Niches components on the left, they're actually quite large. And what we want to do is we want to take this challenge of compressing, the design of these quantum transmitters and quantum receivers down into small, shoebox-sized satellites. And on this picture on the right, you're looking at my research team assembling a model of SpookyOne. And the idea is that if you can actually get the satellite smaller, you actually reduce costs in a number of ways. Launch costs, for example. Now rideshare for nano satellites is actually very common, but also one can actually think of building up constellations much more quickly. And so we decided to take on this challenge of putting some kind of quantum transmitter in space. And the first challenge we did was to say that we want to go and put on an entangled photon phase source, right? We're not really satisfied with just taking a laser and attenuating it. We want to go all the way to put an entangled photon phase source in it and demonstrate that this entangled photon phase source can actually work on a very small satellite. And the main motivation is because quantum communication beyond QKD is about entanglement distribution. If we are ever going to move to a stage where we have quantum computers around the world and we want to connect them in a quantum internet, we would need to distribute entanglement such that entanglement correlations are stored in all these remote locations. And so for us in Singapore, we felt that the real prize is to pursue entanglement distribution, which at the same time can do QKD. Now, in this picture over here, you're looking at a traditional setup for an entangled photon phase source. Typically, what happens is you take a pump laser, a blue laser, for example, what you find inside your Blu-ray player, and then you send this blue beam into a special crystal, and this crystal would then, take some of the blue photons and split them into two lower energy photons. And then one of these photons will go to the left, one of these photons will go to the right. And the correlations between these photons is described by this equation over here. And so if you want to do QKD, what's going to happen is that you will measure the photons on the left and on the right, and you try and compare those correlations. And in the satellite model, you will keep one of these photons on the satellite and the other one you transmit down to the ground. So we've been studying this quite a bit, and we've also decided that we want to show that this technology is feasible for an urban environment like Singapore. And Singapore has the additional challenge that we are in the tropics, so we have a lot of cloud cover. And if you have clouds, you can't do optical transmission. And so we've also been studying space weather and also the cloud cover over Singapore to understand what are the optimum times. And we've discovered that, early to late mornings, like between midnight to 5 a.m. is usually a good time for clear skies in Singapore. And you look at the fact that, the technology allows us to generate 15,000 secret bits for every pass of the satellite. And the number of possible passes that we have, that we can actually end up, using a nano satellite, we can end up with 510,000 secret bits. Now, these are secret bits. This is not bits of data that's being transferred. in the AES system, the symmetric encryption systems that I mentioned earlier, they usually only use chunks of 256 bits. So you can imagine that you can take this 510,000 bits and then chop it up into 256 bits long, and then you can actually, and this will act as a buffer with which you can actually consume, right? So it seems like it's actually quite feasible, even as a real application case. So this is why we are pursuing this technology. And you know, I've been working on this since I came back to CQT in 2010. We launched SpookyOne in 2019, which carries one of these miniature entangled photon sources, right? And it's been working really nicely. And what we want to do next is see how we can put telescopes on the satellite so that the photons can be transmitted out of SpookyOne. Now, if you take a quick look at SpookyOne, what are the internals? Here I removed the solar panels from the satellite. And you can see that the experimental package is this 20 centimeter long unit, and is a 10 centimeter cross section over here, right? And inside this little package over here, it contains all the electronics that you need for entangled photons, right? It has all the single photon detectors that you need. It also has this source of entangled photons that's being produced. And you think about it, this is quite a remarkable achievement, because the traditional picture mounted on an optical table, you can just look at the number of holes over here. And each of these holes is about 1 inch in separation. So you can see that this is actually quite a sizable device. And what we managed to do is compress it down so it fits inside a nanosatellite and it still survives the rigors of space. Now, the main objective of SpookyOne was not to transmit the entangled photons out yet. We are one step away from that. The main objective was to show that the entangled photon generation will continue even after we have put it into space, right? So in order to get into space, what we had to do was package up the entire satellite, right, with the source, send it to Japan, because the Japanese Exploration Agency helped us launch it to the International Space Station. Once on the space station, the satellite had to sit in storage for a few months until the astronauts had time to deploy it. And once they deploy it, we can start the experiment. And the experiment really is looking for the quality of entanglement that we generate. We use a parameter known as the CSHS value, and we can't exceed 2 square root 2 of that value. But what we see is that, very early on after the satellite was deployed, we managed to get a really nice high quality value. And it's been, stable all the way since then, right? In fact, the satellite has been operational for over 2 years in space. This has exceeded our expectations. We actually expected the satellite to only, have the electronics surviving for 1 year, but it's been more than 2 years, and it finally re-entered the Earth's atmosphere on October 15, and that's when we stopped the entire mission. But all the way, we managed to demonstrate that the entangled photons were being generated with very high quality as well. Now, the other thing that we did was also to look at some of the effects of radiation in space, right? And we could see that there was a slow buildup in the radiation damage, for example, in the single photon detectors, but it was not something that prevented us from actually carrying out the experiment. And one of the next things we want to do in space is, understand how to actually correct for this radiation damage. There are some ways where we think that we can actually heat up the detector, and using this heat, we can actually anneal away the displacement damage inside the devices, right? And this graph over here is just a quick plot showing you the altitude drop for SpookyOne over the 2 years. Now, finally, I just want to talk about some follow-on projects. We are now actively studying telescope designs that can fit onto a CubeSat. This is an example of a concept that NUS has been working with Spectral, our spin-off company, together with MIT and the University of Arizona as well, to understand how such a small, quantum-capable telescope could actually be put onto a I think it's an exciting time for us to explore how to put quantum technologies into space, because as the ground networks are being built, sooner or later we will need to link up, these ground networks around the world. And the best way we have at the moment is to use satellites. And why stop at one satellite? We can also talk about constellations of multiple QKD satellites. We can study what is the best orientation for the satellites so that they deliver the best QKD service or entanglement distribution service around the world. We can think of inter-satellite communication. And we can also think of even more advanced experiments where we want to put quantum memories, where, for example, we can actually store. Imagine you have an entangled photon source with a quantum memory. Now you can actually transmit one photon down to the ground, and then the other photon goes to the quantum memory, and then the satellite would then travel to another part of the globe, and then you can release that photon down to that ground station. Now this way, the two ground stations don't always have simultaneous line of sight to the satellite, but can still enjoy entanglement distribution. So these are concepts that we still want to do research on, and we're pursuing that with partners around the world. Yeah, so I think with this, I'd like to end my talk, and I'd like to thank all of you for coming and joining us today. Thank you for the attention.
Thank you, Alex. Thank you very much for this very clear and very informative talk. Alex, I'm sure there will be some questions coming from the audience, and then to start with, perhaps I can ask you, you mentioned that in satellite communication, you can establish about 15 kilobits per pass, and having about 170 or so passes a year. Is this number meaningful? Like, would be good to compare this number to something. So what you said that that's sufficient for secure communication. In what sense? Or what would be a typical usage of the secret bits in usual world?
Right. So I guess what we're comparing against is the size of the secret key that an AES system would consume. So we first start with the assumption that this is a buffered operation. We use the satellite to generate a buffer of secret keys, and then the AES would consume the secret keys periodically as they refresh the secret keys that are being used. So AES uses 256 bits each time they refresh the keys. So all of this 512 kilobits, you can divide it by 256, and you can see how many chunks of AES refresh rates you would get. Right, so this is actually how we would think about it. I think we are a little bit far away from the ideal concept where sometimes people think of, how should I put it this way, securing every bit of data transmitted with every bit of QKD secret key, right? A one-for-one or one-time paired transmission. This can only happen for certain kinds of low bit rate communication. For example, perhaps communication and control systems for industrial plants. But for the vast bulk of data that we're transmitting, the bit rates are so high, the single photon detector simply cannot keep up. From my perspective, the real bottleneck in the technology, in quantum communication technology, is not the transmitters, it's not the entangled photon pair source, it's not the laser transmitters, but it's the fact that the single photon detectors themselves are actually quite slow.
Right. So you say that if you were to point the finger, that would be just the speed of the electronics and photo detection in this particular case to improve this technology. Right. So another question is, you mentioned very briefly about nanosatellites being more cost efficient, but surely there must be some drawbacks. So how would you compare pros and cons of using nanocubes as compared to, say, the Chinese niches?
Right. So there's several pros and cons, and let's start with the cons. right? It's size, weight, and power swap. Nanosatellites are very small. They have very small size. So you really need to think very carefully about how you're going to redesign your instruments that go on it. You can't carry a lot of weight, right? And the power generation is limited because satellites generate power from solar cells. And if you're just using the surface of the small satellite, then you're very limited. Having said that, there's new technologies where you can put some deployable solar panels, like wings that folded onto the satellite. And then when it's in space, those wings open up, so you have a larger surface area. But even then, this volume that you have in the nanosatellite is small. So what we've done over the last 10 years is actually a lot of engineering of the entangled photon pair source and the electronics such that it fits inside the small satellite. But of course, having said that, once you get a handle on how to actually miniaturize the components in the small satellite, you can actually have a faster iteration cycle, because launching small satellites into space is relatively easy. And I'll give you a real example. We tried to launch a test quantum device back in 2014, I think, if I remember correctly. It was on a shared mission. It was a small package, about 10 centimeter cross section with 2 centimeter height, and it was on a Danish satellite. The rocket carrying the satellite blew up, right? So we didn't get that experiment into space. But what happened was that we very quickly built another copy of that instrument and put it onto another small satellite. And then in 12 months, we got it into space. And this only works because nanosatellites have a common standard with which you can interface the components. And so it's actually very easy to switch from one satellite to another one. If we had been working with a big satellite, a custom satellite with special arrangements with the rocket provider, you will not get a fast turnaround in 12 months.
Indeed, yeah. Alex, we have one more fundamental question here from the audience. So Ted Johnson is asking, in the Alice and Bob example, how does Bob know that the photon has or has not been interfered with? So maybe you can, I know it's going to sort of like the basic of QKD, you touched very briefly up on that, but maybe just say a few words how that works.
Well, essentially, there's a couple of things. When Alice chooses which photon to transmit, right, she chooses the basis, if you would. So if you think of polarization, we often say that horizontal and vertical polarization is one basis, and then there's the diagonal basis. So Alice will choose which basis she's transmitting in, right? And Bob will also try and guess what basis she's transmitting in. And so, half the time he'll guess correctly, and half the time he will guess wrong. And so by comparing the statistics of what is wrong and what is right, they can actually build up an assurance that, the photons have not been interfered with, over the entire chain of communications. So it's a statistical process. It's very important that you have enough quantum signals with which to make this estimation. In fact, this is known as finite key analysis, and it's a very important part of QKD. In fact, very early on, there was the assumption that relatively short strings of detection events was sufficient to make this error estimations, but that's been proven not to be correct. And so we are tightening up the assumptions. And so nowadays, we are very sensitive to the length of the detection events, so that we can actually make sure that we get the error estimation correct.
Yes, indeed. So in terms of international collaboration, another question is, who are the major players in quantum satellite communication? Well,
I think the Chinese are definitely ahead of a lot of people. Okay, they have MISHUS, right? In fact, MISHUS is their flagship, but they've also actually put quantum transmitters and quantum technology on some of their space stations. And some of these space station QKD transmitters have been working, although it doesn't seem to have caught a lot of public attention. So the Chinese are definitely ahead. The European Space Agency is now starting to take quantum communications from satellites very seriously. The entire concept of quantum from space actually was promoted a lot by our European colleagues, but they didn't get much funding until MISIUS was demonstrated. But now I think it's a good time in Europe to be working in this space. The Canadians also have a relatively large mission called KeySat. And all of these missions are actually looking for international partners and collaborators. In Singapore, our approach has been to partner with as many people as possible, and also at the same time to build our own concepts for quantum communication from space. And our concept really is based on nanosatellites. And what we're trying to do now is, we're also trying to build an optical ground station in Singapore, with which we can also talk to all of these satellites from other countries.
Yet another question, Alex. Thank you for explaining this. So, are any large companies also involved in quantum satellite communication, or is it only just small startups?
I think it's actually a mix. If you look at in Europe, all the big players are involved, like Airbus and all the others. They're all part of the consortium that's building this. I think it's an exciting time where big companies work with small companies, also with academia, because well, in academia we have a lot of upstream knowledge and basic IP. There has to be a way to transfer this to industry, and sometimes the best vehicle to do that is to have a spin-off that does it. So like that's what we did in Singapore. We have Spectral, which is a spin-off for my group. Actually, a lot of the folks that you saw in the photo that I put up earlier, they were with the university in those days, but now they are over at Spectral, and they have collaborations with international companies about how to actually use quantum key distribution to secure their communications, and how to use the satellites to enlarge the footprint for quantum safe communications.
So another question that we have here is, can this technology be used for free space communication over shorter distances on Earth?
That's great. Yeah, definitely yes. In fact, a lot of the research that we did in Singapore was built on the first free space quantum key distribution exercises. So when I was a PhD student, one of the projects we worked on was distributing entangled photons through free space telescopes. And so this is actually kind of useful in the sense that if you don't have a fiber presence at your endpoint, so for last mile connections, you can actually use the telescopes to do free space communication. And then there are other concepts where you can think of having ad hoc networks. For example, you have aircraft or drones that you need to communicate securely. You can actually use the free space techniques to actually distribute secret keys or quantum signals to these platforms.
Thanks, Alex. I'm sure there would be more questions, but some of them may be conveyed to you via email perhaps later on, because we are going to be beaten by the clock soon. So Alex, thank you so much for joining us for this first OIST seminar or webinar on quantum cybersecurity. It was great to have you as the first speaker, and I think you gave a fantastic overview what is waiting for us for the satellite communication in not too distant future. So thanks, Alex. So what I'm going to do before I just close this session is to perhaps mention that the second seminar or webinar on quantum cybersecurity will take place in January. It's 28th of January. If you're interested, save the date. Najwa Arai will be talking about how should we modify our tools, cryptographic tools, in the context of quantum computers and also machine learning. So Najwa is chief cryptographer at the Technology Innovation Institute in Abu Dhabi, and I'm sure that we will learn a lot from her. So thank you, Alex. Thank you, everyone, and have a good day.